So we are talking about potential energy diagrams, and we were trying to do a potential energy diagram for an endothermic reaction. Is that right? So in an endothermic reaction, again, you need the y and the x-axis. This is going to be your time or your reaction coordinate, right? The reactants are becoming products type of a thing. Is that right? And on your y-axis, you will have your energy. And your energy, the units can be kilojoules, it can be kilocalories. Is that right? Now, you have to label your y-axis. Let's say this is 10, this is 20, this is 30, that's 40, 50, 60. Did I stop till 60 last class? I saw that in Gabriela, so I'm going to do the same thing again. All right? So now, let's say the reactants are at 20. Let's assume the reactant can be wood, it can be anything, all right? It can be the gas in your Bunsen burner. Oh, that's an exo, so it's not going to be wood also. It's going to be something that will actually absorb energy. Is that right? This is an endothermic reaction. Is that right? Not wood. Wood burns. It's exothermic. It gives off heat, right? Or let's assume it's a cold pack. Have you ever seen a cold pack? So you break it open, it solidifies, and it's really cold, and you can apply it to your muscles, right? So something like that. Say such a reactant is present, and the total stored energy within the bonds is 20 kilocalories. Are you with me? Now, just like wood doesn't become ash by itself, you have to start the reaction. Is that right? What is that starting energy called? Anybody in class? We labeled it. We gave it a name. It's a vocabulary word. Yes, Grace? Activation energy. Doesn't matter if it's an exo or an endothermic reaction. Every reaction requires an activation energy. Okay? All the reactants have to be given energy to get started. Are you with me? So then the reactant will climb up in its energy and it will reach the peak. What is that peak called? It's again a vocabulary word. It's called an, whatever is at the top called. There is a picture at the very last page that should tell you what it is called. You should know this. The very last page. There is a diagram. What is the top thing called? In the bottom half, I can see a name written there. The top of the curve. What is it called? Activated complex. All right? What it forms is an activated complex right here. Are we good? All right? And then now, after it's reached so much of energy and all the reactants, the elements are all rearranging and becoming products, it's now coming down, and let's say it becomes a product right here. Are we good? Did we finish drawing this? Now, what is the energy of activation? For this reaction, if I ask you to calculate the energy of activation using this graph, how will you calculate? Activation energy is always what minus what? Top of the curve minus reactant. So it's top of the curve minus reactant. So what is the top of my curve value or the activated complex value? What is it? According to this graph, what is it? What can we assume it to be? 50? Shall we assume that is 50? Okay? So that is a 50. What is my reactance energy? 20, right? So what is my activation energy? 30 kilojoules. Are we good? Yeah. Now I want to calculate the heat of reaction, delta H reaction. As the reaction is proceeding and reactants are becoming products, how much energy is released or absorbed? How will I calculate the heat of a reaction? What minus what? Product minus reactant. Product minus reactant. What is the energy of the products according to the graph? What is it? 40. What is the energy of the reactants? 20. So what's the difference? In this case, it is positive 20 kilojoules. Is that right? If you compare it with the graph that you drew last class, that was negative. This is positive. Does that make sense? The reactants will absorb energy before they can become a product. Okay? So this positive value indicates the endothermic reaction. Or in other words, to conclude that the reaction is endothermic because the product has absorbed energy. Yes or no? The product has absorbed the energy in order to become, the reactant has absorbed to become the product. The potential energy of the product is greater than the potential energy of the reactant. Do you all see the difference between what a graph for an exo looks like versus a graph for an endo? Does everybody see the difference? So when you look at a graph, you should be able to say, the last class when we drew this, now I don't remember all the details, but here the energy is released. The product is lower in energy than the reactant. Are we good? Do we understand the difference? Okay. Now, we have learned what a catalyst is in biology class. What is the definition of a catalyst? Yes, Ms.Geeta.
It's something that neutralizes a reaction.
It is not neutralizing. Yes, David.
Something that speeds up.
Speeds up a reaction. Catalyst speeds up a reaction. It's meant to speed up a reaction. But in chemistry, you learned this last year. We have a lot of catalysts inside our body that helps the digestion process. All right? We eat breakfast, we come to school, we have this energy to walk, to talk, to move. Is that right? Even to think, right? That energy is coming within our body, at our body temperature, without the food burning and without us realizing that all this energy is being created because of the presence of catalysts in our body. Even though the temperature is low, the reaction is still proceeding quickly. Does that make sense? How do they speed up a reaction? How does a catalyst speed up a reaction? That is the question using the potential energy graph. What does the catalyst do? Okay? A catalyst lowers the activation energy and speeds up a reaction. Does it make sense? All right? The energy required to start a reaction is lowered because of the presence of a catalyst. And how are you going to show that in your graph? Have you written this down? What does a catalyst do? It lowers the activation energy. Now, how do you show that impact? So this is my graph. Is that right? A catalyst does not impact the starting energy of the reactants. Whether you had sunny side up or you had bagels, that energy is not impacted until the food enters your body. Is that right? Once it enters your body, it has to become energy in your body, right? So what will the catalyst do? This energy that you need will become lower. Does it make sense? The top of my curve minus my reactant, that difference has become smaller due to the presence of a catalyst. Is it making sense? So this dotted line, what is this dotted line? It's the effect of a catalyst. A catalyst will lower the activation energy. Okay? So here is my question. Is the amount of energy that is released during the reaction impacted because of a catalyst? Or in other words, I've calculated that 20 is my heat of reaction. Are you with me? It's product minus reactant. Has that changed because I added a catalyst? Has it or has it not? It has not. Right? So it doesn't impact how much energy you can get from a food item. It only allows the reaction to proceed faster because it lowers the activation energy. Okay, it lowers the activation energy and does not impact heat of reaction. You should know that. Okay? So in a reaction about, say if it's an exothermic reaction, show the effect of a catalyst on this reaction. What is the effect of a catalyst? You start with the energy of the reactant, you end at the energy of the product. Does that make sense? What you should do is this height should now become lower. That is the effect of a catalyst. Do we all understand how a catalyst impacts a reaction? Okay, we are going to answer some questions, all right? All of you look at this graph. This graph, X plus Y is my reactant and Z is my product. This graph all has alphabets, all right? But I'm going to introduce numbers also so that we do it both ways, all right? I want to do it using numbers. I'm going to call this 0. I'm going to call this 50. I'm going to call this 75. I'm going to call this 100. Write numbers down also. Write the numbers down. We're going to use alphabets and numbers to answer the question. Is that clear? So I'm going to call on students and we're going, if you don't know, it's okay. We're just practicing. Is that right? Don't get ruffled if you give the answer incorrectly. All right? Just going to try. So David, the first question is asking which of the letters in the diagram represents the total energy of the reactant. Remember, this is a graph, right? And where is your X plus Y? Right there. Is that right? What is the energy of the reactants, David? 50 if you look at a number. But if you look at an alphabet, let's say this is all in kilojoules. All right? Let's say it's 50 kilojoules. But if I look at an alphabet, what is that alphabet that denotes 50? A. All right? So the alphabet can be A and the number can be 50. Are you understanding? We've used alphabets instead of numbers. Okay. Reno, what is the total energy of the products? Huh? E is correct. And if you choose a number, what will that be? 75. All right? The number is 75. The alphabet is E. Are we good? Anna, do you know where the activated complex is? Do you know which one is the activated complex? Well, you have to start from 0. So it is going to be, well, it has to start from 0 and go all the way to the top of the curve. C. It can be alphabet C, but if you give it a number, what will it be, Anna? 0 to a 100. So it's going to be 100 kilojoules. The total energy of the activated complex is 100. Are we good? Yara, what is the activation energy in this reaction? B is correct as an alphabet. What about number? Huh? 50 to 100, which will be what? 100 minus 50, it's going to be 50. Is that clear? You understand? Margaret, what is the heat of reaction? Heat of reaction, how do we figure it out? What minus what? Product minus reactant. So what is it going to be? 75 minus 50, which will be 25. Is that right? But if you were to pick an alphabet, what alphabet would you pick? F. That is correct. Right? It is F. So now, Abby, is this endo or exo? Has the product gained or has it lost energy? Gained. Therefore, it is endo. Heat has entered the system. It is an endothermic reaction. Now, so they're asking us to reverse this reaction. They're saying, consider, now change this and think of Z as your reactant. And then think X plus Y is your product. Are you with me? Do you all understand? You're now going the opposite way. If you do it the opposite way, Abby, what will be the activation energy for the reverse reaction? How do we calculate activation energy? What minus what? Look, flip your paper and tell me how do you calculate activation energy. Now this is how the reaction is proceeding, mind you. It's starting here and going like that. Are you with me? It's going in this direction. Okay? And how do you calculate activation energy? What minus what?
Top of the curve minus reactant.
Top of the curve minus reactant. So if you're going, this is your reactant, and that's the top of the curve, what is your activation energy?
D minus Z.
No. You're not going to do that. First, give me numbers, and then we'll look at the alphabets. What is the top of the curve?
100.
100. What is your reactant?
75.
So what is the difference?
25.
25. So your activation energy is 25, which will be what? It will be what height? Abby. It will be what height?
D.
D. Okay? That's going to be your activation energy if you're choosing an alphabet. All right, Kristen. What is the heat of the reaction? What minus what? 50 minus 75. Very good. So it's going to be 50 minus 75, which actually turns out to be what? Minus 25. Do you understand that? As an alphabet, what would it be? But you have to introduce a negative before the F. Do you understand why? You understand? Because now it's reversed. Okay? So, Jenna, is the reverse reaction exo or endo? Exo, you got a negative sign. It's got to be exiting. It is an exothermic reaction. Now, Jameson, I'm adding a catalyst. Okay? We've drawn the dotted line. Would the activation energy increase, decrease, or remain the same as a result of adding a catalyst to this reaction? Very good. It would decrease the activation energy. Are we good? Flavius, if a catalyst were added, would the heat of reaction increase, decrease, or remain the same? We talked about it. Go to your previous page. We talked about how we calculate heat of reaction. What will happen if you add a catalyst to the heat of the reaction? Okay, let me go back. Let me show that. What is this? Let me go back. So, this is my heat of reaction. Is that right? This minus this. Right? I added the catalyst. Now I wrote something else also. What did I write? Does not impact the heat of a reaction. It is important to process this information. Are you processing it? Are you understanding why it is not impacting the heat of a reaction? Okay, so let's go back and let's say, choose the answer that it will remain the same. Are we good? Okay, I need you all to draw the next graph yourself. All right, do it at your station, and in 1 or 2 minutes, I'm going to draw this graph, and then you can compare your answer with what you've drawn. Go ahead, process that information. They've given you the potential energy of the reactants. They've given you the product. They've given you the activation energy. Draw the graph. So, can I go over the answer now? Have you had a chance to process the information? Okay. So they say the potential energy of the reactants is 100. So I'll draw a line here and I will call this my reactant. The potential energy of the product is 50. So I will call this line my product. We have said activation energy is 25. So I have to increase, or the top of my curve is 25 more than my reactant. Is it making sense? All right. So how will the reactant increase? It will rise up and then it will drop down. Are we good? It's going to go up 125 to 125. Do we understand this? So, Zachary, is this reaction exo or endo? It is exo. It's gone down. Therefore, it is exo. Grace, what's the value of the heat of the reaction? Very good. 50 minus 100. It's going to be a negative 50. Right? It doesn't matter if it's an exo or an endothermic. I have to reduce the activation energy. It was originally what value? What was the activation energy? 25. I have to decrease that number. So now I can draw a line like that. Is that right? It's no longer 25. It's something less than a 25. Does that make sense? That height is no longer a 25. Is that right? It's a little more than 100, which was the starting for the reactant. Is that right? But it's not, doesn't go up to 125, it's less than that. Does it make sense? Do we understand? I'm gonna stop this right now. Let's